Dear readers, I am Dr. J. Balavijayalakshmi, co-author of this book. I will discuss about the magnetic properties of nanomaterials. Nanoscience and nanotechnology mainly depends on nanomaterials. The study of nanostructures and the use of related technologies is a rapidly expanding field of study that spans several academic disciplines. The novel properties of nanostructured materials could be understood by knowing the structure and its interrelationship with properties. Some important microstructural characteristics of nanomaterials are grain size, distribution and morphology, nature of grain boundaries, nature of intra-grain defects, composition profiles, across grains and interfaces, residual impurities from processing. The mechanical, electrical, magnetic, thermal, catalytic and optical properties are few of unique characteristics of nanomaterials. These characteristics are unique to nanomaterials which do not exist in their bulk form. The unique characteristics of nanomaterials can be related back to their relatively small size. The study of magnetic properties of nanomaterials is very much important as they are potential candidates for several applications such as magnetically assisted targeted drug delivery, spintronics, magneto-optical device fabrication, contrast agent for MRI bioimaging. The vibrating sample magnetometer is a device which is used to study the magnetic properties of nanomaterials. This magnetometer is based on Faraday's law of electromagnetic induction. Hope everyone knows what is Faraday's law. It actually states that an EMF is induced in a coil when there is a change in flux linked with the coil. The various parts of the VSM are electromagnet or superconducting coil and power supply. Vibrator, we have a mechanical vibrator shown here, detector, coil and Hall probe, and we have a lock-in amplifier, power supply, and everything has been connected with the computer system. This describes the block diagram of vibrating sample magnetometer. The sample is fixed at the end of a sample holder rod, which is placed vertically between the two pole pieces of the electromagnet. The electromagnet generates a strong uniform magnetic field. The sample holder rod is attached to the electromechanical vibrator which moves the sample up and down at the set frequency. The stationary pickup coils are mounted on the poles of the electromagnet in such a way that their symmetry center coincides with the magnetic center of the sample. The change in the magnetic flux caused by the vertical movements of the magnetized sample induces a voltage of the pickup coils. The electrical signal collected from the pickup coils is integrated using a Hall probe. The resultant signal is proportional to the overall magnetic moment of this sample. This procedure is repeated for different values of H0 in order to complete a cycle of magnetization, and the corresponding output signals are converted into suitable values by the software to plot a hysteresis curve. That is a plot drawn between magnetization and magnetic field strength. Hope you don't know what you mean by hysteresis. It's nothing but the phenomena in which the magnetic induction B lags behind with respect to the magnetizing field H. This hysteresis curve helps us to find the saturation, magnetization, coercivity, retentivity, and anisotropy of the samples. The samples may be in the form of thin films, liquids, powders, and bulk materials. A typical magnetization curve for ferromagnetic material is shown in the figure. So this hysteresis actually occurs when an external magnetic field is applied to a ferromagnet such as iron and the atomic dipoles align themselves with it. Even when the field is removed, part of the alignment will be retained. The material has become magnetized. Once magnetized, the magnet will stay magnetized indefinitely. Hope everyone know about retentivity. It is nothing but the property of the magnetic material to retain magnetism even in the absence of magnetizing field. And also coercivity is the magnetizing field needed to demagnetize the magnetic material completely. This magnet's coercivity and saturation magnetization level determines how powerful it is. This figure shows the VSM measurements for zinc oxide nanopowders. To have further insight about this, you can refer the chapter 8. The applications of VSM, vibrating sample magnetometer, have a wide range of application in the field of electronics, data storage, magnetic sensors, actuators, and magnetic refrigeration, as well as in magnetic biomedicine. Hope everyone would have understood. Thank you.